All right, here we are ready to do some calculations. Okay, here are the slides we were working on yesterday, 2 days ago. So these are the chapter 4 slides, and right now I'm on slide 19. So here's slide 19 for the chapter 4. Chapter 4. So this one, we have the population of all students. It says population, so we know that this shape, center, and spread, all of this is for all individuals. So we can use this number, 1.4, for the center, and this number, 0.15, for the spread, as long as any of these questions are referring to all individuals or an individual, singular, as long as they're not a sample, because then we didn't need to go to the sampling distribution. So we've already, I think we did these two, so I wanted to focus on 3 and 4 again. I think we kind of really rushed through these because we didn't have the table ready to go. So I'm going to do 3 here, and then I'm going to do 4 over here. So both of these have a curve, a normal curve, and so I'm going to draw them perfect bell shapes, always perfect bell shapes. Okay, so both of these are using a variable, and we're going to call it x, that is in terms of their meters tall. That's our original axis. And we're going to convert that to a standardized score. And this is going to be the z-score, which the units are standard deviations, instead of having them in meters. Now we know when we do a standard normal curve, a z-score, the center is always 0. So I always like to start with what I know. I know that's 0. Now because these are talking about, let's see, it says a single student, percentile rank of a student, and 4 students. The languaging here is it's talking about individual, an individual. Sample size 1 or all individuals, meaning we use the population mean and standard deviation. Okay. So center is 1.4. If this question had asked about a sample, the languaging would have to let us know how many. So there would be something in there about a group of 10 students or a class of 20 students. There would be some size allotment that would be built into the questioning. Now my bell curve should be identical, but we don't have to be identical on a sketch. At least I'm not. Okay, so here we go. So the first one says percentile rank, and it says that the percentile rank of a person, a singular student, 1.5. Now I know 1.5 would be above 1.51. Now I know that the calculations that we did in class that were on the slide, it says 1.3. It got an error somewhere. So percentile rank is everything below. So our percentile rank would be down here. So that is what we need to know. That is our unknown, is our percentile rank. How much area would be here? We need to know that. That's the unknown. On this next one, here, let's get a different color. This one says the 90th percentile. So that's 90th percentile would be the bulk of our curve would be over here. If I write the area, it has to be a proportion where it's a decimal. 90th percentile or 90 percentile rank would be 0.9 would be our area up to a certain point, and it's going to have to be on the larger side because we know half of the curve is a half because the whole thing has to be 1. So we want to know the meters tall. So this first answer up here is going to be percentile rank, so it's going to be a percent rank for the answer. And the second one down here, our answer is going to be something in meters. Our answer is going to be, because it says the 90th percentile for students' heights, so it's going to be a height, whereas this first one is going to be a percentile. Percent. Okay. So sometimes, we draw our curve first, but we've got to find another area. Let me get a different color going on here. What color should we use that we don't have up here? We've got green, red, blue, let's do orange. So on this one, I'm going to shade I'm going to color in the other part. This is the beyond. And then this one, it's still on the upper right hand. These are both beyond. Beyond the z-score. So on our one where we were given the percentile, the area, we know that all the area under the curve has to total 100%. It has to be 1. So from that, we can subtract. If there's 90% to the left, to the right has to be 10%, or 0.1. This beyond z area, we need to look up in the table to get a z-score. So in this one, we were given an area, so we can find a beyond area to look up in the table to get z. Number 3, it's the area we want to find. So we can look up the beyond area if we know the z-score. So these are both backwards. If you draw and shade a normal curve with the information that you know, can help you figure out, am I going to be calculating a z-score to go to the table and get the area? Or am I going to have an area that I go to the table for to find the z-score? So let me see. I'm going to save this so we can come back to it. I'm going to put this on my desktop. Desktop. I am blind. I'll just put it on my GitHub. Okay. Yes, we'll put it there. Okay. Now, if I go back to our class Canvas page, the Z table and all the other tables are in the back of your textbook. But in the files, I have now placed, and I probably should organize this a little better. There's a formula sheet, but there's also the statistical tables. And you are not going to need this for the exam this time, but if you would like to print them out and have a copy, here's with one way to do it. So here is our Z table. Now, for problem number 4, it said the 90th percentile. So we know we have 10% in the beyond Z. So we've got to go into our table and find what z-score partners with the beyond z part to be 0.1. So if we come down this column, it starts with 0.50 and it gets smaller as it goes down, but it only goes to 0.34. So we got to go to the next column. Beyond z, we're looking for 0.1. Oh, this whole page is too much. Got to go to the next page. Beyond z, looking for 0.1000. Okay. Now, I've gotten all the way to the end, or all the way to where I've passed it. There is not an entry in this table that is exactly 0.1000. This one's close, and this one's close. But neither one of them are perfectly. The 0.003 is 3 tens, hundreds, 3 10,000ths too much, and the one below it is 15 10,000ths too little. So it's in between these two. Our beyond z is between these two. So I'm going to get a color here so we can start. Come on. Doesn't want to work. Okay. One more try. There we go. So we are trying to find 0.1000, and it is in the beyond z. It's in between these two numbers. So then we know our z number. This column was z. This is our beyond z. Our z-score is going to be between those two numbers. So if the computer, R, SPSS, whatever calculator is going to be doing this problem, it would come up with z equals 1.28 something, something, something. But our table doesn't go that exact. We only can go to 2 decimal places. So in this scenario, you can go with either number using this table. It's probably closer to 0.28 than it is 0.29. So I'm going to go with the closer one. Sometimes the back of the book answers are funny. They sometimes go with the closer one. Sometimes they split the difference evenly. Sometimes they use the decimal from computer software. The grad students who made the answer key were not working together. Anyway, so there's our z-score. So for the 90th percentile, in order for us to have 90% to the left, we have to have 10% to the right, and that means that our z-score is 1.28. So let's write that down. Z-score equals 1.28. All right. Now the other problem, we needed to find a z-score first. So let's go back to where we were at. Sketch. I just saved it as sketch. Okay. All right. This is where we were before. Okay, I'm going to get a marker. Okay. So this is number 4. They gave us 90th percentile. So we knew the area to the left was 0.90. The area to the right was 0.10. That gives us a z-score of 1.28. Something, something, something. Now we have the z-score. We went from area on the left, area on the right, which is beyond z, to a z-score. Now we can finally circle around and find what is the x value that goes with the z value. Number 3 is the reverse. We are given an x value, so we need to convert it to a z value. Z value is, the formula says x minus the mean over the standard deviation. So that would be 1.51 minus 1.4 over 0.15. Now this is, I'm going to do these actual numbers, and I'm using my cell phone because that's the only calculator I have. Here we go. 1.51 minus 1.4 is 0.11 divided by 0.15 equals 0.733. Now, I could go to more decimals, but in our table, we only use z values to 2 decimal places. So we know our z value is 0.73. So now we need to find, well, we want to find to the left the percentile rank. But we can look up the beyond z and subtract from 1. So let's see, let's go back to our table. And I had those open here. No. Oh, it was in Canvas. That's right. So our z-score was, oh, I didn't write it down. 0.73. The z-score was 0.73. So now we need to know what beyond area goes with a z-score of 0.73. So back to the first page we go. Aha, there is a z-score of 0.73, and our beyond area is 2327. It also, that middle column says that from the center to z is 0.2673. Go back to our notes. Okay. So, number 3. is in terms of meters. Z is in terms of standard deviations. Our number that we were given, 1.51 meters. Converted it to z-score, we got 0.73. When we looked that up into our table, the beyond area, it tells us is 0.2327. It says that the center to Z is 0.2673. And here's a bonus question. How much area is from the center all the way to infinity? It's half the curve. The whole curve, it adds up to 1, so this would be 0.55500. So there are actually at least two ways to come up with our percentile rank. One way, if we want to do this, is to add those two together. The other way is to subtract this from 1. Both of those should give us the answer of, let's see, 76.73. Because it said percentile rank. Now, if I add those two up, 0.5000 and 0.2673, this is our probability or our area. This question asks for percentile. So to make a probability into a percentile, we move our decimal 2 places. There we go. Okay. Erase that all. Okay. This one was different. We said we had 90% percentile. So that says that the other side has to be 0.10. To get that, our table in the book, well, the closest it said was our Z was 1.28. So now we need to find what's our X. We can plug it into the formula, Z equals X minus mu over sigma. So Z is 1.28 equals X, we don't know, minus our mean of the whole population divided by a standard deviation. Okay, steps. Get X alone. First, we need to get rid of the divide by 0.15 by timesing 0.15 on both sides. That's gone. So calculator says 0.15 times 1.28 equals 0.192 equals X minus 1.4. How do we get rid of the 1.4? It says minus, so we will plus. And our answer comes out to be X on this side equals, and over here we get 1.592. And our answer is a height, so it's 1.52 meters. Okay. Feel much better about the time spent on that problem now. All right. I'm going to come down to this problem. This is the one that's not done on the slides, and I want to make sure that you guys can all know how to do it. So these are, population is the same. There's only one population here. So I'm going to write on this one the population distribution. And the other one I'm going to write is the sampling distribution. Okay, so this is in terms of height. We're going to use the letter X in terms of meters for both of these. We know that the center is 1.4. Now, we said this before. The average of the averages is the average. The center of the sampling distribution is the same as the center of the population distribution if we had all-knowing power. The spread of the population distribution is sigma. The spread of the sampling distribution is sigma divided by square root of n. This is also called the standard error for the mean. So if over here in the population our spread is 0.15, here our spread is 0.15 divided by the square root of a sample size. We've got to have a sample size if we're doing a sampling distribution. And we do. This one says a sample of 16. When it says a sample, you need to do a sampling distribution. If it says population, or it implies the word all, or the word one, or an individual, sample size 1, an individual, or all in the population, we use the spread of 0.15. But if our question implies that we have a sample, specifically, it will usually give us a sample size, then we need to divide by the square root of 16 to get our spread. Now, this is a nice number. Square root of 16 is 4, so I do 0.15 divided by 4. Clear it? 0.15 divided by 4. 0.0375. So that's the spread of the sampling distribution. Okay, so the number we're comparing in both of these is 1.63. Now, these are not drawn to scale. Now, in both of these, it wants more than, oh, I got over the top. More than would be shading to the right. It's this beyond 1.63. In both of these problems, number 1 and number 2, both of them are asking for the beyond 1.63 meters. I should specify that. But they're going to have a different z-score because the first one says a randomly selected student individually 1. So we would, to convert this to z-score, we'd take our 1.63 minus 1.4, divide by the square root of 15 for this problem. The second problem, it says a sample of 16 students. Not all of them, and not singular one. A sample. And so when we do our z-score over here, the top numbers are all the same, but the bottom number needs to be 0.15 divided by the square root of the sample size. And that's the difference between these two problems. It's very slight in the wording. So in this first one, we get a z-score of 1.53. And the second one, we get a z-score of 6.13. Very different z-scores. Very, very different z-scores. So let's go to our z-table and see what it says. Okay, so this one, come back. There we go. Number 1, we had a z, it's because I don't have it. Okay, well, let that go. First one, we had a z-score of 1.15. So I'm looking for z 1.53. Found my z-score. So for the first one, the beyond z, but on that would be 6.30%, or a probability of 0.0630. 0.0630. The second problem, though, our z-score ended up being 6.13. So here I'm going. I'm scrolling to the next page. We got z-scores in the 2s. Uh-oh, I ran out of z-table because, see, it goes to a different table. This is the end of the z-table. Notice it's 4. The biggest z on this table is 4. And beyond, if we go out 4 standard deviations, the beyond 4 area is 0.00003. So how much is it beyond 6 standard deviations? If I had a normal curve, here's the center. If I went out 1, 2, 3, 4 standard deviations, this area out here, it's not to scale, is 0.000, 4 zeros and a 3. So what would it be like if I went out to 6.13? How much area would be left in this tail? Not much. It would definitely be less than 0.00003. So here is a little note. That beyond area, that's like a p-value, the chance of being more extreme. If you get a big z-score, it translates into a tiny beyond area, a tiny p-value. Just let that roll around in your brain for chapter 5. So the answer, if we go to questions, probability that a single randomly selected student is more than 1.63 meters tall, 6.3%. It's rare, but 6%, not that rare. What's the chance that if we take a sample of 16 students and their combined average is more than 6.3? That's like minuscule, very, very tiny. Yeah. So the way you would write this, if you were like doing this for homework, let's see. So this one, we had a z equals 1.53, and that translated to a probability that was 0.0630. But on the second one, we had a z-score of 6.13, and that translated to a probability of less than 0.1, 2, 3, 4 zeros and a 3. Notice both of these questions ask probability. If it wants a probability, you leave that decimal there. It's going to be point something for a probability. So there's the examples for the slides. And I will make another recording that has questions somebody asked about how to do 4B number 6 on the homework. So on to that one. Let's see. Stop recording.